Hi, everybody. Thank you for coming here today. So, yeah, we're here to tell you about how Apache Lucene, helped us to build a merge on refresh. It's a new feature in Lucene. And since we're such an intimate gathering today, I was going to ask for a show of hands. I can hardly see you all, but I'm curious to know how many of you have ever contributed to an open source project? I'm seeing hands. That's great. How many Apache projects? Oh, one or two, yeah? Well, we're a small crowd, so that's great. So I think you'll all learn some interesting things today. Let me first introduce ourselves. I'm Mike Sokolov. I'm currently the program management chair of Apache Lucene. That's just kind of a fancy title that means I make a quarterly report to the board telling them about our progress for a year, and then someone else will take it over. I'm also a principal engineer in Amazon Product Search, and I used to work there with Mike.
Yeah, so I'm Mike Froh. I'm a software development engineer at Amazon. As Mike said, I used to work on product search, and prior to that, I also worked on AWS Search Services, the team that brings you Amazon Elasticsearch Service and OpenSearch. And I also worked for a time on Amazon CloudWatch.
Okay, so this talk, we're going to tell you about this new feature, Merge on Refresh. And when we do that, we are going to learn some pretty low-level details about the Lucene indexing stream, index writer. Stuff that I think very few people in the world know, because it's, it's deep in the system. And then we're going to tell you about how did we share that with the community, what's the process like of opening an issue, getting feedback, going back and forth, getting tests sorted out, and we're going to go through the nitty-gritty of, sharing code in the open source world. You'll find out if you haven't done it before, it might look all sort of shiny and perfect from a distance, but if you get up close, you'll see it's a little messier than that. So, just to set some background for what our day jobs are, why we got into this. Amazon Product Search is the search engine that delivers results to the, familiar product search page where people buy products. And it used to be written, served by a search engine that was developed in-house at Amazon over many years. In about 2019, we migrated to a new engine that's built using Lucene. What is Lucene? Lucene, probably most of you know, or you wouldn't be here, would be my guess, but it's an open source search library. Many people haven't heard of Lucene itself. Lucene actually is the name of the wife of the original creator of the library. Not everyone knows that. But most people are aware of the services that are built around Lucene. Mike mentioned a couple of them before: Elasticsearch, OpenSearch, Apache Solr, which is the open source search engine that used to be built together in the same project with Lucene. Now it's split on its own top-level project. We use it at Amazon in our product search, but it's used in many, many websites that I'm sure you've used. I'm not going to name names here today, but I think it's safe to say that Lucene is probably serving more different search applications than any other search engine. Amazon's committed to supporting its development. We have 7 committers today, employees at Amazon, and 20 or more contributors. A committer basically is just somebody who has been working in the community for a while, made some contributions, done enough work that they've gotten what in the Apache community is called merit, and then have been voted in to have the commit bit, which just means that they can push code into the repository. So let me just tell you a little bit about how the search engine architecture looks at Amazon. What you see here is the indexing half. Over on the left, the product catalog. So updates come in from there, new products, deleted products, updates, and then are indexed in what is called here a writer silo. We have a cell-based architecture. Silo is our word for a cell. So it's the deployment unit. Those are deployed to ECS in AWS. We build on lots of AWS services. It made our job so much easier. So we really focus mostly on the in-process, but So the writer, you can see that the documents are partitioned into multiple partitions. That enables us to scale horizontally, so as the index grows, pretty typical architecture for an index. Then they write those indexed documents to their local storage, replicate them up to S3 where they become durable. Then the searchers get a message from the control plane that there's a new snapshot of the index available. They pull those updates from S3, read them, write them to their local storage, read them in, and open them up for searching. I just want to point out a thing about this architecture that's a little different than the way other search engines work, like OpenSearch, for example. You can see that they're searcher silos. There are actually multiple ones there. We call those replicas. So we scale up by adding replicas. If we want to support more search traffic, we can add replicas. If we want to support a larger index, we scale horizontally by adding partitions. But to support more traffic, we go deeper by adding more silos. The interesting thing about this architecture is we can do that without adding any writer silos. We scale the searching and writing independently. And that's a super nice feature for us. The reason we can do it is that unlike Elasticsearch, OpenSearch, and others, we do replication based on segments in Lucene. So segment is just an indexed set of documents. We'll get into a little more detail about that later. But a more traditional system would replicate at the document level. Because indexing and searching is all done together on the same node, those updates have to go to every node in order to be searched on those nodes. So we save some effort here. We don't spend as many resources indexing, and we can scale independently. So that's a nice feature of the system. And then S3 gives us the durability. So yeah, with that, I think I've set up the kind of background for the understanding of the problem, and I want to hand it over to Mike to get deeper into the work that he did on that.
Thanks, Mike.
Yeah.
So I'm going to start off first with a brief overview of how search engines in general work, and how Lucene in particular handles search. I'm going to cover a variety of topics at a super high level, skipping over the messy details. And then I'm going to dive a little bit deeper into the particular problem that we faced, and then I'm going to talk about how we solved that. So the things that go into a search engine are called documents. The things in a relational database are rows. In DynamoDB, they're records. And in a search index, they're documents. In Amazon Product Search, our documents are products. So here are a few Amazon device products. If we want to let customers search on product titles, the first step is to split the individual words in the product title. We call this tokenization, and the output are tokens. We then normalize the tokens. In this example, I've just lowercased them. In the real world, we would probably do other things. For example, stripping S's from plurals, or stripping verb endings. But for this example, lowercasing is sufficient. So the result of the normalization we call terms. And the collection of all unique terms across all documents is sometimes called the term dictionary. Now, if we assign a number to each document, which Lucene does internally, we can then map from each of the terms in the term dictionary back to the documents that produce those terms. This is called the postings for the term. And the overall structure is called an inverted index. This is kind of the key piece that makes a search engine work. Now, at search time, user submits a search expression. We then do the same tokenization and normalization to the individual words in the search expression. Then, from the resulting terms, we look in the term dictionary, grab the postings for each term, and then intersect them in order to find the documents that match all the terms. Lucene makes this term dictionary lookup and postings intersection very efficient. This is something that has been optimized over many years. Now, on the indexing side, most modern indexing, and certainly the way that we do it, involves writing with multiple threads to take advantage of the many cores that modern CPUs give us. So, to avoid needing to coordinate between threads, Lucene basically lets each thread write its own kind of mini index, which, as Mike alluded to previously, is called a segment. Now, the work in progress segments that are being produced by the indexing threads aren't searchable while they're still being produced. This is, Lucene follows a write once model, so things that are changing are not visible, generally. So periodically, these work in progress segments get flushed, and the writer thread actually doesn't stop work. It basically just kind of hands off its work in progress segment to whichever thread's doing the flushing, and then immediately starts on the next segment. This provides very good throughput. Now, there is a little bit of coordination required, because once we flush the segment, we need to update the global set of searchable segments. Lucene calls this the segment infos. And there's a little lock on the segment infos, indicating that access to the segment infos is synchronized. Well, write access to the segment infos. This is going to be important later in the talk. So what if we just kept adding more and more segments? In an extreme case, what if every document ended up in its own segment? Well, then at search time, the searcher would need to iterate through all the segments, basically sort of asking like, oh, do you match, do you match, do you match? It effectively would become a linear scan, right? We would lose any benefit from that inverted index. So to reduce the total number of segments, Lucene will periodically take several small segments and merge them together into one bigger segment. Now, since the segments are write once, it can safely do this without touching any mutable shared state. The merge thread builds up the new output segment, and then only needs to acquire the segment infos lock for long enough to remove the small segments and put in this bigger merge segment. I like to think of it kind of like Indiana Jones, swapping the idol for a bag of sand, except that in this case, the merge is kind of swapping a bunch of small idols for one big idol. So having multiple segments also helps us at search time, because since each segment is effectively a disjoint subset of the documents in the index, we can use one thread per segment to parallelize. Now, from a throughput standpoint, you'd get your best throughput by merging everything down to a single segment, because that gives you one big, highly optimized inverted index. But that would hurt you from a latency standpoint, because each search would have to basically single-threadedly run through that large segment. Since in Amazon Product Search, we're very latency sensitive, that's not an option for us. So we fan out across multiple segments, and you get the best latency benefit when all the segments are sort of the same size, right? Because you don't benefit from having a thread complete on one of these little tiny segments very quickly when another thread is still processing one of these bigger segments. So we really want to try to balance out segment size as much as we can. You can sort of lower the ceiling by tuning the merge parameters to reduce the maximum segment size for a merge. But how do we raise the floor? How do we increase the size of our smallest segments? So this is where we really get to the problem that we faced. We commit frequently, in order to make changes visible, right? Like, changes come in, we want to commit them, replicate them to S3, get them onto searchers as quickly as we can so that customers are able to see updates to the catalog. But since we have many writer threads, when we commit, all those writer threads flush at once. And because we're doing this quite frequently, the segments that they flush are pretty small. So what we really need to do is kind of merge them before they're visible on the searcher. So the first thing that I tried was just to simply say, OK, well, we commit, then we'll merge, and then we'll replicate. The problem is that you don't actually see the merge segment until you do a commit. But since we still have writer threads producing new work-in-progress segments, when we commit, we just get more small segments. So yeah, that wasn't going to work. Another option that might have worked would have been to commit, stop all the writer threads, merge, and then replicate that. But we have such a high update volume that even pausing for a few seconds to merge a segment just isn't practical. So what we realized was that we needed to modify Lucene itself to kind of put the merge inside the commit. And I realized that in order to do that, I was going to need to learn a lot more about how Lucene merges and commits work in detail. So let's start with merges. So we compute a merge involving several input segments. We hand that off to a merge thread. The merge thread takes those input segments, merges them, producing the output segment. And then it acquires the segment infos lock, swaps, the thing I was talking about earlier, and then it releases the lock. OK, yeah, that's not too bad. What about a commit? Well, commits hold the segment infos lock for a bit longer, because first they acquire the lock, they run through all the writer threads, and flush each of them. Then, and update the segment infos by doing so. Then they take a copy or snapshot or clone of the segment infos, hold that aside, release the lock, and that copy of a segment infos pointing to segments that definitely exist on disk, that's the output of a commit. So now how do we put these together? So first we have to remember that what we commit is what we replicate, which is what we search. So we need to compute the merge while the commit still holds that segment infos lock, right? Because if we release the lock and then tried to compute a merge, maybe new segments got flushed, and those segments aren't part of our commit. We also need to make sure that we don't hold the lock while the merge runs, partly because the merge may take several seconds. We want to minimize the amount of time that we spend holding that segment infos lock. But then on top of that, as I discovered when I had a failing unit test, it would also create a deadlock, because if the commit thread is still holding the lock and we kick off a merge thread, the merge thread won't actually be able to finish because it can't update the segment infos. Then we need to make sure that when the merge completes, it updates the segment infos that's returned from the commit, the copy of the segment infos. So what does that look like? Well, this is kind of a big, scary diagram. But mostly, it's really just a copy-paste of those two previous diagrams I showed with merge and commit. But the orange boxes represent the things that we added. So as you can see, after we've cloned the segment infos, and we've got the segment infos that represent the commit, we compute a merge over those segments, finding the tiny segments that can be fairly cheaply merged into one bigger segment. We release the lock. We kick off the merge thread with that computed merge. And then we wait for the merge to complete, which we're able to track by sharing a semaphore between the two threads, or a countdown latch. So the merge thread will do its normal merge. And when it requires the lock to update the global segment infos, the live segment infos, we added a callback mechanism. So it would then say, oh, also update this clone segment infos to reflect the removal of these small segments and the addition of a bigger segment. And then, yeah, the merge thread signals it's done. The commit thread is able to proceed, and it's like, okay, here, I've got this segment infos that reflects the merge. So it worked. We made these changes, pushed it out to production. This is a graph from one of our production search indexes when this change went out. As you can see, the total number of segments dropped decently, but on top of that, the variance in the segment count was significantly reduced. So this is nice. It gives us more consistent throughput. And yeah, overall makes scaling a bit more predictable. On top of that, we actually got a secondary benefit related to replication, which is that previously, we would flush all these tiny segments, replicate them over, and then Lucene was just going to merge them anyway, as part of its normal merge process. And so it would merge a big segment, which would then get copied over on the next commit, where, yeah, by merging up front, we kind of reduce the amount of redundant work. So I'm going to hand back to Mike, who will tell us about the journey to open sourcing this.
Thanks, Mike. Yeah. So at this point in the process, you know, we were pretty happy. We had something that seemed to be working. We had it in production. And we decided it was time to share it with the Apache community and get it, you know, merged into the main development branch of Lucene. You might ask, well, why do we need to do that? Why couldn't we just, you know, keep our own change internal to our search service? What was the benefit of sharing? Well, there are a couple of reasons. The really critical one is that, you know, we rely on maintaining an up-to-date copy of Lucene in our service. We want to benefit from all the great work that's going on in the open source community worldwide to continuously improve the service. All kinds of developers are contributing to it outside our company, and one of the reasons we adopted it was because we want to benefit from that. So if we start maintaining patches internally that are in the actual Lucene code base, and you know, we did consider, could we layer this on top of Lucene in some way, but I think Mike has probably convinced you by now that wasn't possible. It really was low-level change that needed to be in the search engine. And so if we maintain all these patches, then we get in a situation where when we want to upgrade Lucene, bring in a new version, we have to apply all these patches we've been maintaining. And over time, you know, that builds up, becomes kind of an untenable situation. You don't want to diverge too much from the main branch. So we really wanted to share it for that reason, selfishly. But there are all sorts of other reasons why it ended up being a really good idea to contribute this back, and I'm going to tell you about some of those. So the journey of some work up into the open source package really starts with, in this case, an issue in Lucene's issue tracking system, Jira. You know, usually we tell people probably the best way to start engaging with the community is not by opening an issue, but by starting a discussion on the development mailing list or even on the users mailing list, just asking a question, hey, you know, do you think that this would be a good idea? Is this a contribution that would be welcome? Because, you know, a lot of times developers will be able to say, hey, you know, we already have that, or here's another way you might think about it. You can get some early read on whether it's worth going to all the trouble. In this case, we had kind of enough inside knowledge that didn't really seem necessary. And anyway, this issue got opened actually quite a bit before Mike did all the work that he just described. Here it's shown as resolved. I kind of patched the open over it because I didn't take a picture back when it was still open. But yeah, anyway, it was opened in September 2019, and I think Mike finally sort of got the thing working sometime in November, December. Anyway, so this issue gets created. And then once you have some actual code to share, Typically, the way that's done nowadays is by using a GitHub pull request. In the old days, we used to share using patch files, and it was fairly controversial to switch to GitHub at one time, but now it's pretty well accepted that this is the best way to share. You can comment, you can have all kinds of back and forth discussion. Most of you are probably familiar with this. But yeah, this is where we go. In this case, we shared the code that Mike had written. He made a pull request, and we almost immediately got some feedback from the community. One of the committers came in and said, hey, I think there's a simpler way you could do this. Do you really need to make these changes in Lucene? Couldn't you layer it on top? And basically the solution that he was proposing, which is something he had already done, was like what Mike described, where he said we could stop the world, run a commit, merge, and a commit, and then re-enable indexing. And that we could have done without making any changes to Lucene, but it wasn't really what we wanted. So anyway, we had a little back and forth discussion with this committer. It took a while to explain what we were really doing, but eventually he got it, and then we moved on. So I then, I'm a committer, so I had the permissions to push this change into Lucene's development branch, and I did that. Well, then, the next day, we got emails from the build server. Apache's runs a Jenkins build server every night that runs all the unit tests. And we had a test failure. And that was kind of a surprise to us because we had run all the unit tests before we pushed the change. I mean, you should always do that, right? And yet there was a failure. Well, we realized, yeah, it was kind of a slight random variation, and Mike kind of looked at it, came up with a fix pretty quickly. Turned out to be a problem in the test, not in the code itself. So we thought, all right, let's just fix it. We pushed a fix for it. But then another committer commented on the issue. This is Nat Nguyen. He's a fellow who works at Elastic. And he said, we're running our unit tests at Elastic, and they run a nightly, they run a snapshot of the most recent copy of Lucene, the development branch, in their pipeline internally, and their tests were failing. Well, we weren't really sure what to make of that because our tests were succeeding. We looked at the kind of test failures he was reporting, and we thought we understood maybe what it was. We pushed another fix. It seemed to fix this issue, we thought. But the next day, it failed again. He reported, well, our tests are still failing. And at this point, I kind of want to explain to you a little bit about how it is that we could keep thinking that we had fixed these bugs, and yet tests would still fail. And it's down to this thing called randomized testing. Randomized testing is kind of a testing technique that is very powerful and especially useful for low-level software, algorithms, data structures, search engines, databases, all those kinds of things. Because so much of the behavior of the system is controlled by the data distribution rather than, as a human, it's hard to reason about exactly all the code paths that exist and how they can combine. So in order to make sure that our tests explore all those possibilities, we use this technique called randomized testing. Let me just give you a couple of examples of some of the things that are hard to test without this. Lucene optimizes for cases where, let's say you have a field where all the documents have a value, but some other field maybe only are sparsely populated. Those actually could be handled with different optimized code paths. Or another example would be a field that has the same value for every document. It's either a 1 or a 0. Or another field that has a wide range of different values. Again, you could have different kind of optimizations. So you really want to explore all those cases across a wide variety of different tests. And rather than writing all those variations in every test, we have a test framework that helps with that. It randomizes many things, settings for the index, how frequently we commit, what the merge policy is, gets randomized. What the codec, or the directory implementation, how the files are stored, there are many different implementations. So we switch those all in a random way. And this is a very powerful technique, as I said. It unearths rare cases. If you run your tests repeatedly, sometimes you'll fail 1 in 1,000 times. So this was so powerful that it got spun out as its own project called randomized testing. I think it's mostly used in Lucene, but it's available. You could use it on your own project. It captures a seed so that you can repeat a failing test. That's a critical piece of this. I mean, you just don't want to have random behavior that you can't reproduce. It's not helpful. But if you get a failing seed, hopefully then in your debugger you can rerun the same test and see what happened. The last thing I'll say about this is that tests should be better than your production code. Like, you should put more energy and thought and attention and care into writing good tests, or at least as much as you do for writing the actual code that's going to run in production. Why is that? Well, the analogy I like to use is it's like keeping your tools sharp. If you want to have sharp tools, you need to have a sharpening tool, which is harder than your tool itself. And that's basically the same story here. I mean, good tests will make your production code better. So in this case, what happened was Nat took the extra effort to share the unit tests from Elastic that was uncovering these failure cases. Now, this was not just, hey, here's my test. He had to actually go extract that test, rewrite it in such a way that it was abstracted away from Elastic's internals and could be run directly on the Lucene code base alone. So it was a great contribution, super helpful, and actually kind of paved the way for all the rest of the work that was to come. This test that he created was very powerful. I don't know if he created it, but he shared it anyway. And it did a lot of random stuff. It was kind of like I would call it a little chaos monkey test. It basically would randomly add documents, delete them, update them, do a commit, do a merge, kick off all these different things, sometimes fail randomly, and did all this on many threads at once, different numbers of threads, everything being randomized. And what that meant was it dug up some edge cases we hadn't considered. So, after we saw this test and ran it many thousands of times, and saw a couple of different failures, it was actually finding failures in completely other parts of the code that people didn't know about, but it still was finding some here. And my initial thought was, well, I think I see how to fix this. Let's just fix it and, we'll move on. But then there was some discussion on the list here. Simon Wilnauer, another longtime committer to Lucene, chimed in, and he said, well, why don't you just revert this, work on the fix, and then go forward. And, this is clearly the right thing to do. We benefit, so Lucene has a very high standard for quality. And I think that's one of the reasons why it has become so widely used, so popular and successful. Because there's really a zero tolerance for test failures. If you have a test failure, you should revert first, fix the problem later. Not every project is like this. I've seen many open source and other projects where there's a certain tolerance for test failures because you might have some big complicated test and occasionally it fails. And the feeling is, well, the test still has some value. It's testing some things in our code base that we don't have any other tests for, and if we remove it, what will test them? But the truth is that if enough of those things pile up, then it becomes a little bit like the boy who cried wolf. You make some code change, there's a test failure, you're like, well, I don't know if that was my change. It was probably one of those pre-existing tests that was failing anyway, and you just ignore it. And so then your tests become dull and useless, basically. They're not helping you to keep your software high quality. So in this case, we reverted. And then we tried again. But let me back up, because if you look closely, so the date on this revert, am I backing up? Yeah, was March 7th. And then the next try was June. Well, why did it take us so long? I gotta say March 7, 2020, we had a lot of other things on our mind. There was a lot going on. And we just thought, what, we don't have to push this right away. So we took a little while. But eventually, or I went too far forward, sorry. Eventually I took another stab at it. I ran those tests, that test of gnats, many times, took the failures, reproduced them in the debugger. Yeah, there was some problems with keeping track of files that get deleted. When you merge the two segments together, the files from the old segments are no longer needed, and so they get cleaned up. But there was some problem with accounting where we were trying to delete the same file twice, test was failing, and it was a pretty small fix. So I was able to fix that. Ran the test a lot again, didn't get any failures. So I'm like, okay, let's try again, let's push again. Well, actually, before I pushed, there were some more comments on the issue. Simon came back. Now, Simon, I mentioned him before, Simon Wilnauer, one of the founders of Elastic, really an expert in this index writer code that Mike had been modifying. And he started asking, like, do we really want to do this? This is pretty complex, this change you're making. Hard to understand. I don't know. I think Mike did a pretty good job of explaining it, but I learn something every time I watch this presentation that he gives. Because it's multi-threading, there's concurrency, there's these locks. It's hard to reason about. And Simon's perspective was, this code is already super complicated, and do we really want to add more complexity to it? At that point, another guy that we work with, Mike McCandless, another longtime Lucene committer, he came into the discussion. He was like, please, this is really helpful. We're getting a real benefit out of it. We really think you should include it. So they went back. He finally convinced Simon. And then Simon was like, well, okay, let's do this. But I'm not really happy with the way we're doing it either. Like, it's kind of there's a lot of custom code in here, and it could be done using some of our existing abstractions, in the code without doing so much new stuff. And so he actually, not only did he raise these objections, but he actually came in and made a whole new version of this PR, more the way that he was describing. And it was cleaner. He opened up the API a little bit, added some callbacks so that the merge thread could report its success to the commit, in a more supported way. And that made it easier, to make the change. I think something maybe Mike hadn't really felt like he could do, change the APIs. And it resulted in a nice, clean version that everyone was happy with. So cool. You can see us sort of patting ourselves on the back here about how great this is. Uh-oh. We thought it was all done. Another failure. This was a really tough change. After a while, a very rare case came up. And Simon says, I don't even know if we can fix this. Basically what was happening here was, let me see if I can remember, the merging was going on, writing its new segment. While it's happening, an update came in for one of the documents that was in that merge. When an update happens in Lucene, it's really like a delete and an add. So basically that document that was getting merged actually got deleted. And yet we included it in the merge that we created, the merge segment that we created. And then when that segment got swapped back in, the document came back. So this meant we were violating a really fundamental tenet of the system, which is serializing the operations. If you delete a document, it shouldn't come back. And there could be other weird effects. So it was very infrequent, but really not allowable. Like we couldn't have that, even in a very rare case. So there was a lot of head scratching and concern. But Simon then came in and he was the only one who really understood this, I think. Other people, you could get your head in there, and even for him, it had been probably a year since he'd been in this code, and it took him a while to get back up to speed. And at this point, I want to mention the importance of a healthy community, because if you've got some complicated code that only one person understands, and that person, moves on, what are you going to do? It's kind of hard to learn at the moment when you suddenly need to fix this complicated low-level bug. So it's really critical. This is one of the healthy things about an open source community, a healthy community, if it's constantly bringing in new people, making it accessible so that new people can learn, how the code works, they're encouraged to contribute, they have guidance from people who've been around for a while, then you can begin to build up the expertise in the system among a number of people, so it's shared, and you can kind of solve these problems together much more effectively than you can if you only have a small number of people. A bus factor, some people call it. Anyway, so yeah, Simon, did finally fix this bug. That was great. And, it got released. So that's sort of the end of the story for this change. I did want to come back to the other benefits of contributing to open source. Not only did we get our change in the package so that we wouldn't have merge conflicts later, we were able to share it with a wider community. Now that it's in Lucene, this merge on commit is available to users of Elasticsearch, OpenSearch, all those many other people who use Lucene. So that's just the right thing to do. It's good for everyone. The solution got better. If we had just kept it ourselves, we might never even have noticed that this weird bug was there because it was so rare. And we would have had some kind of buggy code deep in our system that was occasionally dropping a document or not dropping a document when it should. And as a result of sharing this with a wide open community with all of their testing capabilities and knowledge, we ended up with a better solution. And finally, we just improved the community. We built bridges with people all around the world, working in other companies, and created a healthy community that will eventually lead to better software. So I would encourage you to get involved, find a project, contribute to it. It's not only going to produce good software, but it'll be good for you as a developer. It's good for the community to have more people involved. Especially, Lucene is near and dear to my heart, but any project out there, it's a good way to work. I think that's pretty much all I have to say. So I just want to thank you again. I'm trying to advance. Yeah, thank you.